hiccups here or there. And I need to explain a little bit more. I need to explain some things deeper, which might take some time. So I would most likely want to go on with the theoretical aspects of the session, and then we can look at the more practical session when we are fully, in line with this with the theory. Why I'm saying this, because not quite a lot of us are very much embedded, or have this, software structured paradigm in your experience. So, I'm gonna take things a bit slowly, as you progress. So the outline I was given, the outline that analytics sages gave me, um, had a few things that they want you to go back with after this session, and these things include, basically, is just so that you understand how Rust and Solana logic works and how you can maximize it to your best advantage as an analyst. So they provided they provided a detailed, learning outcome that they want. So if you're writing things down, you might want to write that down. That at the end of this session, you're gonna. This is the. If you're seeing my screen properly, um, so I'm gonna shift this a bit to this side so this can be. I don't want to zoom in too much, so I don't. All right. So the overall objective is to equip on-chain analysts with a deeper understanding of Solana's architecture or smart contracts and how to leverage this knowledge for more effective data analyzing and querying. So this is what I came up with. Now, I was given some very, very focused points to ensure I cover, which the first learning outcome I was given includes that you would have a full grasp of the SVM execution model, understanding programs, accounts, and instructions on SVM. So if you don't know now, SVM is basically Solana virtual machine. And what I saw in that is that I'm possibly going to meet with people who don't have detailed experience in this. So we can't talk about Solana virtual machine when people don't know succinctly what Solana is. So then the second thing I'm to be sure you guys leave here with is to have a breakdown of the structure of Solana smart contracts in Rust. So I talked about this smart contract or the Solana program, how we call it on Solana, the Solana program anatomy, which we are going to look at. Then explore how programs read write to accounts and what data structures are commonly used. So this is the third objective I was given. And then understand CPI, that's cross program invocation, and how it relates to logs and instructions. And then align contract interactions with analytical queries, identifying relevant accounts, events, and program interactions. I mean, all of these are a lot of different, layers of English and grammar, which might be robust if you're just hearing all of this for the first time. And what I want to do with you on the call is to tell you that, or show you rather, that it's not as hard as it is. It's like looking at a job description on LinkedIn or something, and and then you think, oh, I'm not qualified for this. And something I saw a friend of mine wrote on LinkedIn, which I truly believe in, is that sometimes these things listed most of the time are like just a very strong way to present it, a very strong manner to present it. And at the end of the day, it's not always as technical as it looks. So, you're taking a bite of it one at a time, one bite at a time. You get to see that, oh, it's not this hard, it's not this difficult, it's not this, stretchy. You can do it too. I mean, if anyone has done it, it shows that it's very possible. So again, we're going to start off with the first part of this session, and I'm going to tell you, as we start, I have a tendency to talk very fast when we get started. I have a tendency to talk very fast and probably not carry everybody along. So that's why I say, yeah, I want you to talk back to me. So if I'm getting too fast or if I'm saying things that you're not catching up with, please, you can do well to don't write on the chat. I will not be looking at it. Let's have a very, very structured classroom, um, you know, um, scenario, so you can unmute and call my attention to it. Um, so yeah, unmute. You can unmute the mic and don't try to follow a lot of formalities. It's not a university classroom. It's not yeah. So, and I'm not a lecturer, so you can always unmute and call my attention to something you're not catching. So yeah, Solana. What is Solana? Why is it different? um what is what? So, quick one. Let me catch your thought a little bit. I just need one or two persons to quickly tell me when they hear Solana, how what comes to their mind, and how do they differentiate it from other blockchains already existent. So, quickly, one or two people. I want to see what you I want to catch your thought on that. When you hear Solana, what comes to mind? Simple as that. Please don't raise a hand, unmute, and give it to me.
All right. Uh, when I hear Solana, I hear speed. I hear um, throughput, like a very high throughput and efficiency. That's what I.
Thank you so
That's
much.
what comes to my mind.
Thank you so much, Melvin. Melvin says he has speed, he has high throughput, and what again, please?
I hear
And
lower gas fee.
efficiency.
Efficiency. All right, thank you. Thank you.
Yeah.
Thank you. Please, Tara. Tara, go ahead.
Yeah, I was saying low gas fee. Low gas
Low
fee.
gas fee. Low gas fee. That is very important. Low gas fee. Low gas fee. Is that all? Okay, Tara. When Tara hears Solana, she hears low gas fee. Melvin hears speed, efficiency, and high throughput. All right. So these things, in a way, points to what Solana is, and in a way points to what differentiates it from other L1s, like let's say Polkadot or Ethereum, or and the list of them. Now, what really combines, makes up these things is what we are going to look at on how Solana works under the hood. All right. So let's start with Solana fundamental goal. Solana's original goal, all right, is to be a high performance and very scalable blockchain. It's as simple as that. High performance and scalable. So again, work with me. I'm not your I'm not your detailed guy. I apologize if you learn a lot with slides. Probably we can you know create a slide with what I have here. I attempted one here, but I didn't really get it off the ground. But again, it's something we can do together. So just stay with me. If you're with a notepad, please open it, so we're sure we're not missing out anything. So like I said, first, the main goal for Solana is to deliver um, a very high performance and scalable blockchain. Now, this means that we are going to consider speed, we're going to consider low transaction cost, and we're going to consider the ability to handle massive volumes of transactions. So these are the very important components: speed, low transaction cost, and ability to handle massive volumes. Now, this is like the very, very, very low level. I'm trying to speak as low level English as possible. And to really understand how these things work, or to really okay, so since we have identified these things that we're going to be looking at, what do we do? So we then look at how it is originally designed on the infrastructure level. Now, I'm going to be sharing this document because I think it's something we are going to be using. I It was over my head. I would have um, probably shared it with Tomishe so that he could have shared to everybody attending the call, so that you could have probably gone over it. and had a very detailed read before the class, but um, still that's not a problem. I believe we can go through it together. I have dropped this report with on the chat. So if you I don't know if I've successfully done that. I believe I have. I believe I have, right. So it's on the chart. It's on the chart. I can see a couple of thumbs ups, which shows I have. All right. So it's on the chart. So you can download this report. And I'm telling you this to say that if anybody, this is a very detailed report. It's a lot of pages. I can't remember, but I know it's let's control command end. Oh, you want to stop presenting? I'm giving the command on Meet instead of. I'm trying to get to the end. Oh, okay. This is not giving me the page numbering. Oh. Okay, so I printed this document out, right? I printed this document out because I wanted to fully like understand it when it was released. It was written by Lostin. Lostin is a developer relations engineer at Helios. Helios is actually one of the main protocol infrastructure RPC providers that enabling Solana, and in collaboration with Turbine 3. I was a student at Turbine 3 at the time this was written. So at some point, we all had, to see this before it really was published, and had a few contributions to make. So when this was published, I had to print it out and have it to myself as a hard copy, so I could study it. Like I'm reading for an exams or something in school. And what it did is that it gave me a very detailed context to why everything happening on Solana is happening the way it is happening. So if you're not opening these yet on your PC, please do, because I think we're going to cover everything we need to do following a structure like this. Um, you know, I'm very lazy, so having something like this, and what's the point of having a slide when we have this? We can work with this. So yeah, we can work with this, and yeah, I can leave it with you, and then so yeah, um, into it. So we see how Solana's very particular about high performance, low latency, and speed, and all of that. Everything we have talked about earlier, and then we are looking at how this approach works, because okay, how blockchains basically work is a bit different from how Solana works. It all boils down to the infrastructural layer, and this is what decides how programs are executed on the layer. All right, this is what decides how programs are executed on the layer. So Solana takes integrated approach to blockchain development, leveraging the founding team's decades of experience building distributed systems. So now, I wouldn't want to read this word for word. I would love to go into the parts that really like concern the things that I want us to talk about on this call, which are, number one would be, the key architectural components that we need to figuring out what makes what work the way they are and how they are different. Please, after this call, I implore you to take out your time and study this document for yourself. If you're looking at doing anything on Solana for a long term, like I always say, the tiniest details of documentations like this is what do you call them, the bad characters leverage on. Is what the bad characters leverage on. So the first part of this particular documentation talks about the transaction life cycle, which is something I'm going to omit because that's not what we need. All right, I'm going to omit that. But I implore you to look at it. I implore you to look at it. So it's basically how transactions are done on Solana. And then I want us to start looking at things like this. So now we're going to look at Gulfstream. And then we're going to look at Gulfstream. Then we're going to come here. You're going to stay with me. We look at these core concepts together. I'm going to run through a very quick description of what each of them stand for. And the things I want to really want you to pay close attention to are the proof of history, to our BFT, the Gulfstream, which we're starting off with, the sea level, and the pipelining. So these are very important. If you're writing, look at it. We are looking at the key components that makes the Solana infrastructure relevant or functional in the way they do, the key components. And then we are starting off with Gulfstream, which I'm going to look at in the document we have open already. Then after that, we're going to look at proof of history. We're going to look at our BFT. We'll look at sea level and pipelining. Now, looking at these things, I highlighted them because they, in a way, have distinct paradigm structuring than what is on Ethereum, which is very popular. And one of them is going to be looking at how we handle meme pooling on Solana, and how it's being done on Ethereum. And then we are going to look at the actual direct differences. Then we go into looking at the account models. So first, Gulfstream. What is the Gulfstream? What is the Gulfstream? Okay, so Gulfstream basically functions like the mempool. Okay, so what is a mempool? Um, in Ethereum, basically, let me explain this. In Ethereum and just probably every other blockchain infrastructure, when there are a lot of transactions, happening, what happens is that there's a pool where these transactions are being held, and so that they can be distributed to a free validator to handle that transaction at the moment. So this gives room for some transactions to be on a pending state. So we see here that in traditional blockchains, each node reserves a part of its memory for memory pool, more commonly known as the mempool. So the mempool is used to store transactions that are currently being broadcasted over the network, but not yet added to the block. Now, the process of adding to the block means it has been processed and added to the block. Now, who processes and added to the block? Who processes transactions and add them to block in proof of stake blockchains? Basically, the validators. All right, so we're not looking at what is blockchain. I believe we understand what. Please, do we understand what validators are? Proof of stake, proof of. Do we get that? Can I see hands in the air? Do we understand that, right? All right, I'm seeing. Theophilus, please. You have a question? Okay, no question. So now I want to be sure. You have a question, Theophilus? Can I continue? All right, no question. So now handling this in this particular paradigm creates an overhead, right? And how does Solana solve that? It solves it with a Gulfstream. Now, Gulfstream is basically a mempool-less solution that forwards. Okay, what exactly Gulfstream exists to do is to create a parallel transaction paradigm, such that transactions happen on a parallel paradigm where nothing is pending. There's always a validator available to handle the transaction at every given time. So instead of having single shared mempools, transactions are being pushed to the next expected leader. Now, this would make us want to come back here, and might want to make us want to like come back to on Solana, transactions on Solana, which is something I want us to like bypass. So basically, um, every transaction life cycle starts with a user initiating an instruction, because transactions are basically instructions. So it starts with the user initiating an instruction. It could be a basic swap from your phone, and then blog is created and then propagated, to the chain, and this would be, executed by a validator and then added to the chain. I mean, we understand that. Now, how do these things happen? It happens in 6 phases. So there's no way we are going to be talking about this, how Solana infrastructure works, without looking at this. It happens in 6 phases, and we see it detailed here. Where the user initiates a transaction, what happens is that once a transaction is initiated, this goes into the system and it's being processed at the Gulfstream. All right. Understanding this 6th phase, which we're going to look at, and then going to account structures would give us a lot of in-depth knowledge on how we, in the last part of the class, when we get back to, having understood this and understood programs itself, and, the Rust IDs and the, raw structures. So what do we do? How does the interactions work? What do we look out for? So follow me. So users initiate or start a transaction, and it goes right into um, the Gulf Stream. All right. So okay, let me zoom out a bit. Um, how is this thing minimized? Uh, is affecting my vision. Who knows how I can minimize the Google Chrome or the Google Meet pop-up? I feel if I cancel it, it will just close. Let me just take it to a side and then
It's 20 hours.
okay, I've handled that. So now, so we've talked about how a user initiates a transaction, and all of these details is not what I'm going to be doing right now on the call. You can read the details if you have specific things you want to look out for there, which I believe you should after the class or after the session. So there's a user initiated action, and there's RPCs are activated. RPCs take on the user instruction on chain, and is being handled in the Gulf Stream. Now, what are RPCs? I don't know if okay, so it's not developers, it's not contextually developers. So we have finance guys here. So let me detail it a bit. So RPCs basically are like nodes. Basically they're like nodes that take information to and fro the chain to users, and so that messenger that you tell what to do to text some, and it takes that information on chain and gives you a response, that kind of thing. So these nodes are thought of as gateways that interact and read data from the network. You need to really understand this, because we're going to get back to RPCs. So they run the same software as full validators, but with different settings, allowing them to accurately simulate transactions and maintain an up-to-date view of the current state. At the moment, there are about 4,000 RPC nodes currently running on the Solana network. And then let's get here. Solana stands out with it because it was designed from the onset to operate without a mempool. I explain what a mempool is. Now, unlike traditional blockchains, that use gossip protocols to randomly probably propagate transaction across the network, this how Solana does it. So there is a leader. There's a Gulf Stream leader schedule that nodes pass information to, who then the leader then disseminates this particular instruction to available nodes that are ready to available validators. Now, don't forget, validator nodes, okay, validators and RPCs are both nodes. All right, so don't get it mixed. So yeah, so RPCs take in information to the Gulf Stream, and it gets to the leader, which disseminates it to the validators. I wouldn't want to talk about this year's stake weighted quality of service is a model that is being used to decide who takes on the next action. So it's based on who has the most stakes. I don't want to deal on that, but this is more like a diagram of what really happens. All right. So this is what the app where the users interact with passes information directly to the RPCs, which then takes it directly to the validators. Now, the validators makes up the Gulf Stream. So the validator with the highest stake weighted quality of service becomes the one that processes the information at the time. So it's a little bit of it's a simple what do you call it now, model. But if you're just seeing it for the first time, you might need to like go over it again. So the process is dApps, users, whatever, send information on chain. Now, what is really on chain now? Now that is what we are looking at. The Solana infrastructure broken down. All right. So RPCs are the ones that receive the information directly your from your dApp. All right. It could be a swap, it could be to send some Solana to somebody, it could be any information whatsoever. And then it takes it directly to the Gulf Stream. All right. The Gulf Stream is basically made up of validators and a leader. So the leader is the validator with the highest stake, who then processes and gives out to the node with the most option to check on the transaction at that given point in time. We see that we have 500 open connections shared by all, and then we see node validator 1 has 1% stake with just 20 connections. Validator 2 has 40 connections. Validator 3, and so we see how the information flows through the most relevant validator at the moment for processing. Now, all right, so I'm gonna quickly skip this. All right, okay. All right, so I don't want to detail into, because this is not like a software class, so I will have time to go to the other parts of what we are doing. I don't want to detail into the direct connection models that these validators connect or transact with each other, but the quick nodes and whatever you'll be seeing here are basically normal model. I think I did a very solid thread, very detailed on the quick node, and even what they call it, Netflix, I believe Netflix and YouTube also utilize this quick networking protocol for sending information among their servers and their clients. That's everybody that's using Netflix, and the server itself, and how they transact information and how you receive what you're watching, and all of that, and all of that, and all of that. So this tech itself, I don't want to go into that. But the main thing for you to understand here is that RPCs take information to the Gulf Stream, and the Gulf Stream is processed in a way that the information do not stay hanging, waiting for transaction to happen. There's always processing going on within a round of validators, who the leader of the Gulf Stream would appoint to take on the transaction, depending on what validator is available and ready with more stakes at the moment, because it uses this stake weighted quality of service to ensure that they are being processed and in a very secure format. So now, moving on, if we come back here, we would see here that Gulfstream is a mempool solution for forwarding and storing transactions before processing them. So instead of having a shared mempool, transactions are being pushed to the next expected leader. This allows the next leader to quickly receive transactions and start processing them immediately. Basically, the thing I just said, and process or show diagrams of from this other document. Now, another thing I want us to look at quickly is sea level. All right, sea level, or okay, let's look at sea level from here. I don't wanna because I think it relates a little bit more with So sea level is a runtime developed by Solana team that allows parallel processing of smart contracts. It can process many transactions as many cores are available in the system. So these major improvements make Solana multi-threaded globally. Now, basically, sea level is another mechanism you might need to understand when dealing with Solana infrastructure on a very detailed paradigm, because, by the way, let me share this core concept link with you as well, so that you can be sure to look into the process. So that is actually from a full Solana program that you might want to check on if you're interested building Solana products. So this is just section 2. There is a programming model, then there is the program library, then I think there is the Solana introduction. So if you don't know what Solana is on a very basic level, you can see what is blockchain, what is infrastructure, what is transactions, slots, epochs, ecosystem, smart contracts, and all of that, yada yada yada. So coming back here, I believe we were at, oh my god, time is running so fast. I don't like this. All right, so we've talked about golf. We've talked about the Gulf Stream, sea level. So I think before talking succinctly on sea level, you need to understand what proof of history is. For those that do not understand, I'm going to quickly run through proof of history so I can successfully explain sea leveling so that you can understand it properly. So Solana doesn't really use proof of history as its core consensus mechanism. At the same time, it doesn't entirely use proof of stake as its core consensus mechanism. So understanding how these different mechanisms come together is what I really want you to get before we move forward. So basically, proof of history is a mechanism that is being used by Solana basically for timekeeping and synchronizing local virtual clocks on all nodes. All right. So I believe by now we know what nodes are. Nodes are validators or basically RPCs. All right. So proof of history is that mechanism that creates that timekeeping protocol for the nodes. And this actually gets to work where we will be looking at time stamping and looking at what time rates are transactions processed and how. All right. So what proof of history basically does that it minimizes, or this direct importance, that it minimizes the block time for eliminating waiting overhead. Thanks to synchronized clocks, communication can be replaced by local computation. So looking at proof of history and the concept of synchronized clocks being programmed directly into how the nodes function and the whole Gulf Stream explanation, it creates, I think it should begin to form a base, even if you've not heard of Solana before, you've not been exposed to this kind of, layers before, layering or layer of information before. So now, I can go on to talk about this mathematical explanation to how the computation is being done and how it affects validators and all of that. But I think it might not be essentially relevant to what we are doing. But understand that proof of history basically is like synchronized clocks that are like wired into the nodes or wired into the functionality of the nodes. Now, coming down to Gulfstream, right? I want to like rush in a bit because time is quite far spent. Because proof of history allows for a global variable timeline, Solana introduces sea level. Now, this sea level is basically parallel transaction processing engine. So it offers it enables parallel transactions. Where's sea level quickly? So it enables parallel transactions on chain, right? So it allows no overlapping transactions to be executed. So instead of having to wait or having to let's say there are transactions that are being sent into a particular validator or to a particular leader, and it gives it out to a validator and is being run. What sea level does is that it prevents um overlaps in how the transactions are being shared. I'm lacking means to probably explain this thing in the most basic terms. Okay, so let me explain why this is crucial for analysis, or it's crucial for analysts. If two transactions, let's say there are two transactions that modify completely separate accounts on chain, now they can be processed at the same time, yeah, all right, but there will be this huge throughput gain compared to a sequential execution model like what is used in the EVM. So I don't know if I'm putting this so in the most basic terms or in the most understandable terms, but I believe that if you like go over this again and try to understand how transact okay, probably when you talk about account models, which I believe we can, is about 813, and then account models and sending transactions on chain, you might probably understand more practically how these conducts operate. But just get it that C level, allows for no overlapping transactions to happen simultaneously. All right, so that there is that parallel processing constantly being run on chain at every given time, 24 hours 7, as the case may be. All right. So another thing I would want us to look into is our BFT. These things are quite very important if you're going to be like working on Solana. So I understand that it might sound quite foreign to you if you're just learning this or hearing of this for the first time. So that's why you need to look at. I'm glad this class is recorded. I need to look into this over again and sit with it, for some time, and understand that this is not just something you are doing for because you're in a group chat and or you're in a committee and this is what they're doing. This is something you're doing for your career. This is something you're doing for the advancement of your knowledge and your efficiency and proficiency and relevance in the industry, basically. So now coming back to our BFT, basically it means Byzantine fault tolerance. um I don't clearly know what it was that this name came up with. It's always like strange to me each time I look at it, and I think it's almost strange to everybody. That's why almost everybody you see on Solana just goes ahead with the whole BFT acronym. So basically it's a consensus algorithm, right? And what BFT basically does is it's like a layer on top of the POH. So POH, proof of history. So it's like a layer on top of the POH that uses the clock. Remember we talked about the clock earlier. It uses the POH clocking system and allow validators to reach consensus quickly and efficiently. All right. So how do I put this now? We understand at this point what proof of history is. We've understood at this point what the gold stream is, and to an extent we understand what sea level is. Now understanding Tower BFT is basically like a consensus that works on top of the POH. And what it basically does is it ensures that transactions are conducted and finalized in the most safe way or in the safest processing possible. All right. So it uses, like I said, use the POH, the proof of history clock, to allow validators to reach consensus quickly and efficiently because they already agree on the order of events. So it's more like a sequential order that allows validators to follow through when executing transactions on chain, utilizing the clocking system. So if you look at it again, if you zone out a bit, you see that all of these, different infrastructural components are all interoperate together, and they are all functional for a single transaction to happen. All right, they're all functional for a single transaction to happen. I would want to rush up a bit so we don't waste further time just looking at the Solana infra basically, and I would want you to again, go into this document. I mean, Lostin did a really good job in the detailing and the illustration in this particular uh documentation. So please go into this, and then you will probably like get a very solid understanding of what it is that I've been talking about all this while. And okay, and then probably when we meet again, because I'm sure we are going to an hour is already gone, and we're not even going headed half yet. So now before we get into account model, which is like looking at the other end of the SVM, I want us to look at what makes, I want to quickly run through this, what makes Solana different from other blockchains. So if you have analyzed anything on another blockchain, what you might be wanting to look at, and how you might want to look at different aspects of analyzing on Solana. So the first thing here is that I want you to understand that Solana is monolithic. All right. So remember me saying that all of these different infrastructural components at the very base layer of Solana all interoperate together, and they're all relevant to make one transaction executable. All right. So it's a very monolithic transaction. It doesn't, stand alone. All right. So Solana is very monolithic, which means that the execution, the consensus, the data, the availability, and the settlement are all in one layer. So there's no, you will not hear that there's a Solana L2. Or obviously, there are like some L2 kind of systems or infrastructure that have been built, but they don't exist independently to make Solana better. They have to function as a core. So Solana is monolithic, and so this contrasts the modular approach that platforms like Ethereum uses, where one particular chain could be handling the settlement, another chain is handling the processing, another chain is handling the security. All right. So the whole blockchain trilemma is being solved in a single layer, and then the account model. So that takes us to this next page now. So the account model is what account model series, or the account model of Solana, is what makes Solana again very, very, very different from every other chain. All right. So I'm gonna enter this part, or close this part with the account model. So what is account model on Solana, and how do we approach this? For starters, right? For starters, um, if you have used, let's say, or Windows or Unix. Windows, I've forgotten what operating infrastructure Windows is built upon, but Unix, Linux, almost everything is a directory. So you create a directory for if you're using Linux, right? Everything is a directory. I think in Windows everything is a file. Everything is a file. So you create a file that houses another file. The file is being read by the system even the folder is being read by the system as a file. So everything is a file in Windows operating system. And same model can also be likened to what we have in the Unix operating system, like the Mac models or the Linux models. On Solana as an operating system, or the SVM now, every single thing. So on the Solana virtual machine, every single thing is an account. So every single piece of data, every single piece of transaction, every single piece of information, anything at all you can think of is an account. It's being seen and recorded as an account. So within a Solana validator, the global state is maintained in the accounts database known as account database. So accounts DB. The database is responsible for storing all accounts, both in memory and on disk. Primary data structure, account index, hash map, making accounts database essentially vast. Okay, so this explains the accounts at the very core. So for the case of the you can still hear me. I want to reckon you can still. All right. So I want to go into account model now. We looked at a few infrastructural component for Solana architecture or Solana base layer infra, and then I want to migrate out of that into Solana accounts, so we can look at Rust programming and the Anchor framework. Before let's see if you can do that before 8:40. So at this point, is there anything I need to explain in detail, or are we good to go? All right. So quickly before I go into Rust, so account model is very important that you understand account models on Solana. So one account is a container that persistently holds data similar to a file on a computer. So like I said, everything here is an account. So everything you're going to be doing, when you finish, if you're a developer, after writing a program, you're going to bundle it and it's going to be read and processed as an account. All right. So we're going to see a ton of accounts, which we have here. So I'm going to quickly look at it. I believe you can see my screen. We're going to look at it together. So there are user accounts, and these accounts have private key and are typically generated by a wallet software for a user. So this is talking about the accounts that your wallet creates for you when you start interacting with a Solana wallet, and this has a private key, and we're going to see the impact, or what private key, or what an account owning a private key has into play. So data accounts on the other end store state information, such as number of specific tokens or a user holds. All right. Program accounts, on the other hand, are larger accounts that contain executable bytecode, somewhat equivalent to a .exe file on Windows or .app file on Mac. So when I said, if you're done building a product, or building an app is going to be bundled into an account. So it's going to be bundled into a program account. And then we have native program account. Now, native program account, all right. So native program account are basically pre-deployed program accounts that perform various core functionalities on the network. All right. So I wish we have time where let's open source scan where I can show you a variation of these different accounts. Time is not on our side. Time is not on our side. So let's get to the class. Let's get to the class. All right. So if you can cover this quickly, I believe on continuation we can look at more succinct examples. All right. So yeah, native program accounts. So these are like run on the infrastructure level. All right. So you mostly will not even have to interact with this. So accounts have the following fields. Please understand this fielding in accounts. So if there's always going to be a field for and format and description. So the owner, the public key address, and the owner of the account by default, the system program. Now this is for the first type of accounts that I spoke of earlier. All right. So this particular user account would be having the owner in the field, and then we have a format that, like, how do you address it or how do you access it to be a public key address and then the owner of the account. All right. And so now the lamport in this case, or the field for lamport now, because every account has this particular details provided here. So the lamport field would contain a U64. So this is like basically integers. All right. And this will basically be the amount of SOL that is being held in the account. And then the next field that every account must have, be it user account or data account or whatever account, is data. What actual data is being held on this account. All right. Now, what actual data is being held on this account? So this data could be in bytes or it could be variables. Now, variable length and byte. Now, if this account is a user account, it will be holding byte here. All right. But if it is a program account, for instance, it would be holding a variable. Now, this is the difference, right? Okay, let me not detail into that. Again, I'm trying to not think or not look at this from a developer perspective. Now, the rent and the epoch, all right? So every account has to hold the rent field, all right? And again, because to create an account, you pay rent. I'm not sure I mentioned that earlier. So when you create an account, rent is being paid. It can be paid without you even knowing, because if you hold a Solana, what's the word now? If you hold a Solana wallet, that means you have a Solana account, and then that means there's rent being paid to keep that account active on chain. All right. So, and that rent is basically always in U64, again, like in Lamport. And then this is the legacy field. This is just a description of what that is. More on rent later. Okay. This for the context of this actual documentation. Then executable. Now this takes us to what I want to talk about when I was talking about data on the account. Now, if the account is an executable account or a non-executable account. Now, for accounts like user account, which is like the ones you use to transact with chain, that's not an executable account. But program accounts are executable because they hold executable bytecode that will be processed, that there's an instructions in it, or there are instructions in it. So if you are looking for data for specific purposes, you might want to be looking at what executable accounts are on a particular smart contract, or what executable accounts are on this Rust smart contract or on this Rust program. Okay, so which of these, how are these programs, how are they executed? Or what programs, what execution needs to interpolate with another execution from another program? That's where CPI is coming. All right. So it's very pertinent that you understand this. And this is always in this type of account, whether it's in the format will be a Boolean, because it will be true or not true. And okay, this would lead to talking about PDAs. But okay, I wouldn't want to jump right into that yet. Let me look again at what we have here and see how far we've covered. Okay, so this is probably where we are now, and we're looking at everything is an account. I've explained that. the breakdown. Okay, this is what I've not. Okay, this is where we are at the moment. All right, and then executable and non-executable account. Then ownership, account ownership. That's for program. Okay, I think I've explained that. Then rent. So every account must pay rent, and we've talked about that. Every account must pay rent as long as that account is running on Solana. There has to be rent paid to keep it running, and this rent is actually can be refunded or will always be refunded if the account ceases to exist. If you are building a product and then you're going to be creating a bunch of accounts for your program, or you're going to be creating a bunch of accounts on your program, and then you're going to be paying for each of the accounts you create. So these are the things that chunk up to what makes what people really pay for when deploying a project or when deploying an app on Solana. All right. So now PDAs. Now the last thing I want to talk about here before I move forward from here, the last thing I want to talk about here is PDAs, and let's quickly look at that. Programs. Okay. I've run over this. I've run over this as quickly as possible. So you can ownership, rent, programs, so these are things I have just run over, and you can do well to like study it closely again. Okay, this is something I want us to look closely so that you can understand what PDAs are. All right. So when looking at storage states, so Solana programs being read-only executive files. Okay, so now let's look at program data again, or program accounts. All right, let's look at program accounts. So Solana programs are accounts that contain only executable logic. All right, so these are like, they actually change state when they are being executed. So they don't hold or they don't hold information, or they don't, they actually change state because they are like running an instruction on the layer, on the infrastructure layer of the program itself. Now, a variation of it is a PDA. Now, what are PDAs? PDAs are basically accounts that are being owned by program accounts. So now, when writing smart contracts, okay, we are already talking about smart contracts already. I think that sets this. I think this sets up the next segment of the the program or the class. So we're already talking about smart contracts. When writing smart contracts, you might need to develop an account to be controlled by the program that you are building. For instance, I'm building something that let's say I'm building something that is let's say a betting platform. For instance, people can come and bet on the outcome of a game, or prediction markets basically. And then in my program infrastructure, I have to write an account, a program that exists, that is controlled by the program, by the software itself, that maybe watches out for a state that let's say if people vote, or if people bet, and then there's a particular amount of people that are in a betting pool, and then when winners are selected, this account should release tokens or to the winners by itself. So I write an account that his job is to, or I write a program, a PDA now, that his job is to release what's it called, tokens to the winners when winners are executed, or when winners are selected. Now imagine that at every point in time, the program I have built will directly handle the PDA inside it to release tokens whenever there's a particular agreement met. All right, so now that is how PDAs work. Now, because it is being owned and controlled by the program that is being deployed already, PDAs do not have private keys. All right, so this is like this place. If you've not gotten anything on account, understand this. So PDAs are programs that are owned by the program that is associated with, not owned by a specific user. And then PDAs take actions on the execution of an already arranged or an already executed algorithm, and they are to be controlled by the programmer itself. And so that means they run without you don't need to validate or sign each transaction that account does. It's very important that you understand how PDAs work, because if you're going to be analyzing a lot of data, a lot of on-chain data, you're going to be seeing a lot of PDA executions and it might be a little bit difficult to decide or track PDA operations, because to really see PDA operations, you need to follow through with the account that owns the PDA. All right. Now, how is this whole PDA thing possible? This whole PDA algorithm is possible because they are basically derived from the public key in this order. Now, this public key in the order of this ED2559 key pair doesn't own a corresponding private key because it is off the curve. Now, these are a bunch of different algorithms or different terminologies that I'm pretty sorry if it's sounding all new to you. Okay, you're in it already, so you'll get to get yourself dirty with this information as time progresses. So now this is a detailed analogy or diagram of how the whole ED25519 curve is created. Now, if you look at this Cartesian plane, where my mouse is, almost all accounts that are being created are created on the layer directly, which means that at every given point in time, there's always a corresponding X and Y, so that we can always have a corresponding private and public key. Now, what we're meaning by off the curve is that the only program that can operate or control it is the program that it's used, because the account is created out of the elliptic curve at this part of the curve that is marked. So it is off the actual Cartesian plane where regular accounts are being created in line. I mean, you don't need to totally understand this whole elliptic curve thing right now, but it's something that you can look into and then get yourself acquainted with it, and probably look up a few other examples. And let me quickly see if I can show you a transaction that is done by PDA. So this is the source scan. Let me quickly let me pick this transaction for instance, and this is open now. So I'm trying to look out for the account. Is this a PDA? Is this a PDA? Let's look at this. Let me inspect this account. Where is the signer? Okay, let me inspect this account. I'm opening this signer. So now, how to quickly see a PDA? You see that this is an account with this address, all right, and this is the sole balance for that account, and then this is token balance in that account. And then looking at more info segment, you see that the owner of this account is system program. So that means this is an account that is owned by an individual. This is actually someone's wallet. And you see is on curve. Now, an of course address is any address which cannot have a corresponding private key. So you see this is that cannot have a corresponding private key. That means if this is true, if this on curve is true, it means this account here does not have a corresponding private key. So while this is a system program, which means it is owned by an account on Solana, you see that on curve is actually true, which means that it is a PDA. So it's not owned by a user, it's rather owned by a program. So that means that almost every transaction that happens from this is not signed by an individual. It's not signed. It's not, the transactions that all of these transactions you see here are done from this account. They are not sent by somebody. They are all sent from a program that owns this particular account. And then this is the program that owns this particular account. So we can see funded by, and then I copy this, or let me just open that for further inquiry. All right. So, you can go into and look at these accounts. It owns about 4.9K in Sol. That's about $2,000 at the moment. And it's also another PDA that is being funded by, now we see who owns it now. So you see that there was a PDA that is being controlled by another PDA, and then it's being owned by the BTC Talk hot wallet. I mean, I would love to dig in a little bit on all of these and all of these and all of these, but god damn, time is far spent, and there's been a lot of conversations, a lot of talks, and I've not heard from a lot of people. So the next phase basically that I would love to jump into would be us getting directly into Rust now, since to an extent it feels like we have some solid understanding of, or some sort of exposure. I'm not sure we have the proper understanding yet, but some sort of exposure to what and how Solana, if Solana virtual machine functions, how transactions work, and the different the different protocol components that make up the monolithic transaction processing that is in Solana, and how data at this level is being processed. So what we are going to be looking at next is Rust. But I don't know, time is far spent. I would want to pause a little bit and see if there are any questions, see if there are any discussions, if there are any things that would, I can buttress on, or things that we need to, look into, or anything like that. I want to be sure that we are all in the same page. And to talk to the admin, I don't know. I don't think I'm a very good time manager. I would rather do this, in a week, and ensure that we are looking at the proper detail than rush it all in one class, and nobody gets, or less people get the full context of what we are trying to do. So I don't know. Has there been any questions so far? Has there been anything that I should look into or discuss about, or what's up? Are we following basically? Melvin, please.
All right. Thank you very much. My question is, we are able to easily spot the PDA on SoulScan. Like, how are you able to easily spot it? Is this from the address, or like how is this easy for you to spot? That's my question.
All right. So to spot PDAs is very simple. So all right. So can someone okay. So now PDAs, understand this, do not have private key. All right. So coming back here to account structure, or to fields, all accounts have the following fields on Solana, right? And then these fields include the owner field, the Lamport's field, the data field, the rent, and the executability of the account. All right. So when you're looking at owner of an account, it has to be a public key address. All right. So it's always this is just a description of what the public key should be. So it's always the owner of the account. By default, most accounts on Solana are system program. So most accounts on Solana are like, you always see it's owned by system program. Even your wallet, you can copy your wallet address and paste it on SoulScan right now. Let me quickly bring on a wallet address so we can. I hope you are still seeing only just the page that is live. All right, so let me bring on my wallet address. I will take the risk for everyone, don't worry. Where was the last time okay, so I'm going to bring in my wallet address here. I really hope that you only saw this page that I left. Please tell me that's all you saw. All right, so I'm going to go ahead and paste my wallet address here. So let's confirm something together. EJ. I don't cast myself. All right, now looking at this. This is the address. So this shows the owner, right? And this, okay, I missed something here. I mixed something up here. All right, so this shows the owner, of the account, and then it goes on to show the balance. The black, please forget about the balance there. Don't pay too much attention to that. What we're looking at is this, please. All right. So on Curve, let me give me a second. Let me pick a PDA here. I interact with a bunch of PDAs, so we're gonna see the difference. Just give me a second. Okay. I interact with a bunch of PDAs. Just give me a second. This is not a PDA. There is a mix-up I did on my end, and I want to correct that right away. So quickly, let's go to transactions. I don't want only sold transactions. Okay, let me leave that open. Transfers. Okay, transfers. Quickly, let's look at the last 20. Okay. Okay, give me a second, please. The last 40. Okay, let me just do this like this. Let me filter the value to minimum of $10,000. 1, 2, 3. Max of 30. Let's filter this. So there's an account I want to demo something with. 28. All right, let me look at this. And then Jupyter aggregator. Let me look at this. Okay. No. I'm looking for the account signer. All right. So this is a PDA now. Okay, I think I found what I needed to see. Now, this is on Curve. You see on Curve, and then you have true. All right. You were the one that asked the question, right? So on Curve, true. Then you look at this other account on Curve, false. Are you following? Look at this other account on Curve is false. Now that's the directive. That's how you quickly spot a PDA. And how is this? This is because PDAs are not on Curve. All right. So they don't have corresponding what's the word? Private keys. So their Curve net level is always false because they are off the Curve. You know what I'm saying? So you see here that they are used to hold tokens and lie, and they live off Curve. So it basically means that when you see on Curve, you look at this account now. You look at this account. It's not, see the public name for the account. It's being owned by the Jupyter program library, and they are used to disseminate rewards like airdrops and stuff like that. And you see that on the Curve level of it is false. So that is how you quickly could spot a PDA. Don't mind you, it has a regular address like this, like every other account. All right. So I think I've been able to detail that. If you have any other question in that line, you may want to ask now. So if you look at any account, when you look at the more info segment on SoulScan, you always have this on Curve. That's where you look at if the account is being owned by someone or is owned by a program. So if you are like looking at to hack, you might want to of security. You might want to what account is running these transactions, and you might want to look at the account itself. If it's like mine, which is true, you might then look at where is this operated from? Is it from a mobile phone? How do I get behind it? How do I access the private keys? Because accessing the private keys basically is the most secure form of communicating with accounts and in Solana basically. So I don't know if there's any other question in that direction. Yeah, Christian, please go ahead.
Yeah, good evening, sir. I was also 5 to 10 minutes, so I couldn't really grasp what these videos are. But from what I understood, from what I could touch on like past 3 4 minutes, um, PDAs would directly be corresponding to like smart contracts and ABM chains, correct?
I
Instead
didn't
of
get that. I didn't get that clearly. PDA's what?
PDAs would be like a direct correspondence to like smart contracts on EVM chain, correct, right?
PDA is a direct. I didn't really. I don't know if you can speak louder. I can't really get that. You're
So,
speaking clearly,
so
but it's not nice.
basically, it's the same question I wanted to ask, right? PDA is similar to contract addresses in EVM.
Okay. Contract addresses on AVM. All
Yeah.
right, right. Yeah, that's a good analogy to look at it from. But contract addresses are being owned by the contract, right? They're being owned by the yeah. That's a direct similarity. I agree with that.
All right, sir. Thank you, sir.
All right. But I mean, there's a lot more to PDAs. There's a lot more to PDAs that you would want to look into. Please, this document here, I would really advise you look into it fully. There's a lot more to PDAs, and you might also want to look. I shared this as well. Programming model, account anatomy. Yeah, account anatomy, is the basic thing that we have talked about here. Executable, account types, PDA. There should be PDA here. Runtime policy, program derived addresses. Yeah. Okay. So yeah, now here you go. It's a lot more. There's a lot more to PDS, and it's very important that you understand PDS. Especially because when we now get to dealing with CPIs, there will be a lot of program derived address operations at that runtime. So it's very important that you understand CPIs because most cross program interactions would be invoked from PDA executions. All right. So it's very important. And in some cases where PDAs handle quite a ton of data, that makes it a lot more interesting. Looking at the logic from that direction. So it's very important. These links I shared, Solana handbook, is very important. I will share this the full thing. So now I think I shared just a segment of it earlier. So Solana handbook, and then the Helios report. I don't know. Can we still cover Rust? Can we still cover Rust? Do we rush on it? Joshua says, here we go. I mean, analytics sages. Admin, are we together? Do we proceed?
Yeah, please proceed.
All right. So okay. Let me grab water. A bit thirsty. Just give me a minute or two. Let me grab water. I'll be back in a jiffy. Yeah, a minute or two. All right, guys, I'm back. So now, back here, we've covered you know, a bit of everything that we set out for in the first segment. So let me quickly get into Rust and why Rust is important. So for this class, we're going to be looking at Rust, and then briefly we look into Anchor. So in the next this 8:54, in the next 10 minutes, I should be able to like close this in. All right, so let's get on it. Rust is basically a very important programming language. We all know Rust is not like a blockchain based programming language like Solidity. Like Solidity or Sui Move, or any of those blockchain built languages. Rust is a native computer programming language, a native language that is close to C. If you've programmed on C or C sharp, or it's the closest to low level programming language that we have yeah, today. And all right, so why are we using Rust? Please, if you've not looked into Rust before, you might want to do that. Rust, let's quickly look into Rust programming language itself, rustlanguage.org, and then you might want to also open this on your this thing. Okay, let me just pick this up. This is my actual workspace. A lot of tabs there. So we're gonna do this for the duration of the class. Okay. So you might want to open this down as well, so that you can get on it practically as we run around together. So why Rust? Getting started with Rust. If you've never programmed in Rust, or you don't really know what Rust is, so Rust is basically another programming language that is very secure and reliable. That is exactly why we are doing Solana with it. So while we are transitioning from what Solana and how Solana does what where specifically to the smart contracts now, which we call programs. So I would be using a lot of programs, Rust programs, Solana program, Anchor program. So when I'm talking about program, I would definitely be talking about smart contracts. All right. So why are we using Rust to write Solana programs? Or why are we building with Rust on Solana? Basically for two reasons: because of its high level performance and security. And so what does this really mean? Performance and security. Rust is Solana actually has a lot of processing. A lot of people are using Solana. A lot of people are processing information on Solana, and therefore it's important that there is error. The error on program error is kept minimal. All right, so that's why the developers or the builders of Solana choose to do something around Rust, because of the how do I put it now, the like we say, the glass chewing capacity, or how close this to metal, than any other language that could be used to program the blockchain. All right, so is that secure? It offers memory safety. So Rust has a very strong memory safety, which can be looked at as garbage collector. What I mean by memory safety and garbage collector, I have a little bit of an issue trying to break these things. Just pop up in my head. It sounds as if I'm speaking a lot of English. Okay, let me try to break it down. So imagine that you're building a program, and then you have there are runtime errors. So what Rust does is that what Rust prevents basically that memory safety without with a lot of garbage collecting, basically means that it prevents like the common programming errors, you know um you know from compiling, rather than it compiling and then being found at runtime. You get? So if there is an error, the Rust won't even compile. So that's one of the reasons why people say that it's harder to build with Rust, because there's some things that there's some errors, there's some warnings that could be overlooked if you're building with another programming language. But those errors like null pointers, those errors like those common differences that could easily just execute and run, and then probably give an error when executed, would not even compile to start with. So Rust goes through that process where you have to compile and test. It has to pass, your program has to pass tests. So that's like the memory safety is very, very important in that line. And then that we are building for financial processing, and there are millions of dollars processed daily, and you need to watch out for any kind of error that would lead to loss in the future. So what Rust concepts are we going to be like looking at efficiently? If you're just pumping in here, you can check in a few Rust documentations. If you want to install it, you can just go to install.
It's 21 hours.
And then copy this and paste, and then follow through this installation. It's basically as simple as what you see here. It's very, very simple, very, very straight. If you want to play around a little bit, you can come right here and try a few Rust commands, but we're not going to be doing that tonight. We're not going to be doing that tonight. We're not writing vanilla Rust. I'm going to tell you why, and then we are going to go into what we should be doing. So we've talked about why Rust is important, and then key Rust concepts that you should understand. One is ownership. The next one is borrowing, then lifetimes, and then okay. What I highlighted here is ownership, borrowing, and lifetimes. All right, ownership, borrowing, and lifetimes. Now, what is ownership? I should have done this here, but I think I would have to complete this just for Rust and then share with you on the group so that we can effectively run around. But what is ownership? Let me just run through this. Ownership basically in Rust, every piece of data has an owner. All right, so every piece of data has an owner. So you see that account concept coming back here. So it's like a book, so you can imagine a book that only one person can own at a specific time. Only one person can have the physical copy of the book at a specific time. So every data that is created on Rust has that ownership, conditioning. So one, ownership, because we're going to come back to this. Ownership. Then the second option I gave was borrowing. So I'm going to still use that book again to explain this. So imagine that the book only has one owner at a given time. So it means that if another user is going to use the book, it's going to be borrowed. So it means now how Rust processes this kind of system is that when data is borrowed, you can borrow a reference data without taking ownership. That's basically what it is here. So you can borrow reference information without taking ownership, and then on execution you can always return data back to where you borrowed from, or which there was a very succinct on-chain example that I can give about for that now. But again, let's just run with the book analogy. So imagine there's this book that only one person can own at a time, and then you give it out. Now there's a construct that decides that the person that is being given or lent, who the book is given to, must read the book to the end so the data must be exhausted. It must be executed before ownership is restored. All right. So again, so there are two types of borrowing here, which one is immutable. Oh god, this is gonna be long and time is far spent. So there's immutable and then there's mutable. All right, so there's immutable and mutable borrowing when working with data on Rust. So what this basically means that the immutable part is that is read only, and then the mutable part is like you can read and write to it. All right, so we are going to look into this a little bit more very soon. So The next thing we're going to be looking at there is lifetimes. Now, lifetimes basically ensure that, references are valid for as long as they are needed. So there is a time space to what data is borrowed, and what data is being used. So again, back to the book analogy, the time space to which I use in finishing the content of a book I borrowed and returning. Now, this concept, while it might be a bit challenging to understand now, right? While it might be a bit challenging to understand now, you would probably understand when you see more examples that, or probably if you're writing Rust or you look at some Rust codes, you might, see more examples on, the more or more useful use cases. Quickly, since we're not going to be writing vanilla Rust, this also, you might not necessarily need to understand all of them in detail, because what happens is that we use Anchor for writing Rust, right, on Solana. So Anchor is like a framework. Basically, that's what it is. It's like React for JavaScript and CSS, or I don't know frameworks in financial landscape to use. So what frameworks basically do is that they embed the critical component that makes or the repetitive components of a particular infrastructure into classes and functions that can be executed via one-liners. And that's what Rust does, or that's what Anchor does. So Anchor encapsulates a lot of Rust commands and makes it easy for us to deploy Rust programs or Rust instructions via macros. So in Rust, there's something called macro. Macro is basically, excuse me, macro is basically when you can, write a set of instructions and encode it into a programmable class that can be, recalled or something. Now, what Anchor does is that it gives you those macros in one lines, so you can exactly deploy, let's say, all right, so you can deploy a Rust program, an entity of a program, by just calling a macro like this. All right, by just calling a macro like this, and then it's that simple. So if you look at the actual Rust code, so let's quickly look at something. So let's look at something. Let's open I use cloud a lot. Let's look at something. For instance, I'm gonna be I don't want to try cloud for rest. So I'm gonna say show an example of program declaration in both native Rust and Anchor syntax. Compare between the two. So let's quickly see something here. Now, this is a lot of code. All right, all right, all right. So now, looking at this contextually, you see how that native Rust program breaks all of these things down in this format with a lot of entry points here to be used just at the declaration level, and then it goes on to encode all of these just to initialize public key and account information for the program itself, and all of that, and all of that, and all of that. And to do this, for every given time that you need to define another program on Rust, you need, or to define another account, you need to go through this lengthy process over again. Whereas on Anchor, basically all you need to do is call this macro, and this is what you get. So if you are, let's say, let me quickly open my okay, at this point I'll need to share the entirety of my screen so that we can see my code base. Where we at? How do we do this? I need to stop sharing this one now. Yeah. Present something else. Present entire screen. All right. Okay. So please don't mind my. So let me quickly create a new not a new file, bro. Open new window. So let me quickly create a new give me terminal. So I'm going to Anchor init. So okay, I have Anchor installed. I have all of these installed. So I'm basically going to initiate an Anchor program now. All right. So I'm gonna call this program. Let's call this program Analytics. Okay, Anchor init Analytics, and I run. Then our Anchor, gets to start creating all of those things that I could have done if I was using Rust on the vanilla level. So we have this one. I believe you guys can still see my screen, please. Hello, hello, hello. Please talk to me. I can't see the.
Yes, we can see it. We can see it.
All right, beautiful, beautiful. So let me quickly open this Analytics, and then we hit open. So we see that we have our full app ready, with everything we need: the node modules, the program, the source, the everything basically. And we have this program ID program already created for us on the lib.rs file. Now basically this is where your Rust files would lie on. So it's on the program here under the initial or the file itself, or the folder, the root folder. You go to programs, and every other thing you would most likely see is a dependency that enables this function properly. So if you're going to be creating more files, you can go right into it and just keep touching and creating more files that you're going to be writing your Rust instructions to. But basically that you would not get that fast. You'll not get this embedded what do you call it now, these embedded commands, if you were going to write vanilla Rust. So that's basically why we use Anchor. And again, Anchor is natively built. It's natively built for Solana itself. It's natively built to run Solana programs. All right. So you might want to come back to, is this where we are at? I doubt. You might want to come back to here and really look into how Anchor programs work. And then what we are going to be looking closely into would be this program structure, because this is basically the smart contract anatomy of every Solana program. So we're going to look into what what is declare ID, what are programs, the program macro itself that of which I've shown you, the derive account, and the account macro. So this is quite a bunch, and of which I don't think I have the tenacity right now to specifically or continue. I know we want to go ahead with the class, but I would want to analytics stage. I would want to see how to minimize my time because I have something else I'll be doing in the next 20 minutes, so I could prepare for that. So
Yeah,
I
please,
want to
you can just start off.
something. I want to solicit for something. Um,
Okay.
this is a detailed masterclass, and it's not something that should be rushed over. So
Yeah.
we exceeded our time for today. I
Okay.
believe if we have another 2 hours like this, we
Yeah.
can, because now we are in the practical part now, and it's very important that we deal with this, with fresh memory and a better understanding of the concepts that have already been taught. All
Yeah.
right. So I want us to approach this on a fresh level because
Okay.
I'm going to be writing code, and I don't want us creating or looking at code specifically where we don't really understand what a PDA is. So pointing it out on code would be difficult, or would be, people will not be carried along, or pointing out, some where an account is interacting with another account on an
Yeah.
existing, program might be a bit difficult. So what I
Yeah.
want us to do is this: let's look at these two materials I provided, these
Okay.
documents, like everything we did in the first part of this class is in this document in the most detailed way. This is the most detailed thing on Solana you ever see. I can guarantee that. It's so detailed that, even if you don't know anything, you would definitely be able to understand a little after reading through it over and over. So if you can look into this and then look into this as well, and then so that when we come on the next, I mean, you guys will give me a date. What I want us to do then would be directly write Rust and then directly run CPIs directly on chain, interact with on chain data, mutate state, which is very important, cause changes to the Solana state, at least on the DevNet level, and see how to, fetch those data. I don't know if we're on the same stage.
Sure.
Yeah.
Sure. Sure.
Yeah. So,
So
so that would be me, wrapping it up, because basically we have touched Rust now, and we have touched Anchor. And if I should go ahead and go ahead and go ahead, I wouldn't complete the things that I have to do for the night. So once again, I really appreciate the time, and you guys have stayed to the end. I mean, you guys are the real MVPs. So yeah, bro.
okay, thank you so much, Udoka, for your time and for that explicit session. And like you've requested, we'll work towards another half, of this session. Thank you so much for your time. I know you're a very busy person. Thank you so much, for joining us and walking us through this journey. All right. Also, special